Hello, in this part of the lecture, we're going to review some key properties of capacitor and inductor, which will be used extensively in the first order and second order RLC circuits. So let's first look at capacitor. So capacitor stores charges and electrical energy, which is proportional to the size of the capacitor or the capacitance. So a capacitor can block DC or constant current, which looks something like this, where this current IDC is independent of time. The charges stored inside the capacitor are linearly proportional to the voltage. So Q stands for charge. So Q is equal to C times V. So larger the C, larger the Q for a given voltage. A capacitor can also pass AC, alternating current, or time varying current. So both of these will be illustrated later. So it's a quick overview here. So I have a time varying sinusoid, which denotes my AC current. And along with that, I have a DC current, which is denoted by IDC. And as we know from before, this IDC is nothing but a constant. The symbol that we can use to represent a capacitor looks something like this, where we have two plates, okay? Or we can draw it in a slightly different way with a curvature associated with the negative polarity. So in this case, we have something called electrolytic capacitor. And for this type of capacitor, you will need to be careful with the polarity. Otherwise, you may end up with some unpleasant experience. The unit associated with a capacitor is farad. And this is also equal to coulombs per volt. Okay, or simply we just use F to denote the unit of a capacitor. The typical range of value goes from 1 picofarad to 1 microfarad. The larger the value, the larger the physical size of your capacitor. The capacitance is also a measure of cap's potential to store energy in an electric field. Right? So a capacitor stores electrical energy, and current passing through this capacitor can be denoted by this equation. So IC is equal to C dVc over dt. And this equation can be simply derived based on the relationship that we just talked about over here. So if we take the charge Q, okay, so we know Q is equal to CV. And we also know that the current I is equal to dQ over dt. So I can simply substitute this Q in here such that I is equal to dCV over dt. But since this capacitor, or this capacitance C, is a constant, so we can simply take this C out. So this will give us C dVc or CdV over dt. And I like to put another subscript C over here just to indicate or stress again the fact that this voltage drop is across capacitor, which is shown over here. So V sub C of T is the voltage drop across this capacitor, and I sub C of T is the current flowing through this capacitor, and is denoted by this equation. So this is one very important equation for you to remember. And we will be using this equation quite a lot when we talk about first order and second order circuits in the time domain. Okay, so again, this equation can be simply derived by knowing your Q is equal to CV. Right? So it's a simple equation that we use to determine the amount of charge stored inside a capacitor. Right? And this is linearly proportional to voltage. So Q is equal to CV. And along with this simple relationship, the current I is equal to the change of charge with respect to time. Okay? So by knowing these two simple equations, we can derive this one over here. Okay, so again, IC of t is equal to C dVc over dt. Okay. So let me give you one example to illustrate this point over here. So how does a capacitor block DC, or how does it block a constant current? Okay. So knowing that IC is equal to C dVc dt, so if I were to represent, so this is versus time. So if I apply a voltage, a DC voltage or a constant voltage, let's say 5 volts. So this is Vc of t versus time, okay? But this is constant, right? So we can say that this is simply just a DC voltage, VDC, okay? So if I apply this equation, okay, so IC is equal to C dVc over dt. So for a given capacitor, okay, I can take the derivative of this voltage. And we know that this voltage is nothing but a constant. So when we take a derivative of a constant, so we have d constant over dt. So this term over here is going to give us 0, right? So a derivative of a constant is equal to 0. So 0 times C is still equal to 0. So that means the current passing through this capacitor is equal to 0. Okay. So circling back to this bullet point here, a capacitor or any capacitor will block DC. Okay, will block DC or block constant current. Okay, and this is the result coming from this simple observation or from this equation. Okay, so if the voltage that I apply across this capacitor is no longer a constant, so let's say this voltage is time varying. It goes up and down with respect to time. Okay, so that's what this means, time varying. So it varies with respect to time. So in such case, if you revisit this term over here, dVc over dt now is no longer equal to 0, right? Because we are no longer taking the derivative of a constant, right? We're taking the derivative of this time varying signal. So in such case, we know that I sub c or IC is not equal to 0. Okay, so in this case, we cannot say this capacitor blocks this time varying signal. Instead, we should instead in this particular case, we'll say that the capacitor behaves like an AC couple. Okay, AC coupling. It's an AC coupling capacitor which passes the AC current, okay, or this time varying current from one end to the other. Okay. Again, in the DC case, no current is going from one end to the other, right? Simply because this capacitor blocks DC, right? Based on this derivation, IC is equal to 0. But as V is now time varying, okay, so this dVc over dt, okay, is no longer equal to 0. So you're going to see some current flowing through this capacitor. Okay. Okay. So let's look at how to calculate capacitance for a parallel plate, a capacitor. Right, so if you recall from your physics class, right, so we have these two plates, and we put these two plates in parallel, one on top of each other, and with some separation, which I call D over here. And in between these two plates, you may also have some dielectric. Okay, and epsilon r, as you know, this is the so-called relative permittivity, okay, or relative dielectric constant. Okay, so C, okay, capacitance between the two plates is equal to epsilon times A divided by D. So where A is the area of the plate, Okay, and typically when we say A, right, we assume that these two plates are overlapped. Okay, there's a certain amount of overlap between these two plates. Okay, so we call that area of the plate A, okay, or the area of the overlap A. So epsilon times A divided by D, and where D is the separation. And from this equation, you notice that if I want to increase the capacitance between these two plates, then what I need to do is I need to try to reduce the separation between the two. Okay, so if I reduce the D, I can increase the C. Okay, similarly, I can also increase the overlapping area between the two plates. So that's another way for me to increase the capacitance between the two plates. Okay. Next, let's look at the relationship between capacitor voltage and current. So a few minutes ago, we looked at this equation. IC of t is equal to dVc over dt. Okay, and here is a little derivation as a reminder, right? So we have Q is equal to CV, okay, and IC is equal to dQ over dt. And from here, from this equation, we can express IC in terms of both the capacitance, and the voltage. Okay. All right, so now we have this important equation, okay, but how do we express the same in terms of voltage? Okay, so, or how can we express the voltage in terms of capacitance? Okay. So all we have to do here is we do everything in a reverse way, right? So all we have to do here is we take the integral. So I take the integral to get rid of this derivative, right? So I need to take integral, and when I take the integral, I ended up having this, right? So I take the integral on both sides, so, and then I move the c to the other side, and now I can express my Vc of t. So on the other side, I have 1 over c, okay? And then integral t0 to t, and then I have this IC of t, okay? So since, I don't want to use the same letter here, okay, so I'm just going to use a dummy variable tau, okay, to denote the time. Okay, so IC of tau, d tau, okay, and then plus another term here, and this is my constant term, which denotes this the initial voltage or the initial condition. Okay, so when I do the integral, I have this initial condition that I had to account for. So if both Vc of t and IC of t are larger than 0, in other words, if they're both positive, then I can say that the capacitor, okay, is being charged. Okay, capacitor is being charged. I'm charging my capacitor with positive V and positive I. If both V sub C and I sub C are negative, okay, then we can say that the capacitor is being discharged, right? So this is the opposite case, right? Well, I can charge a capacitor, and I can also discharge a capacitor by looking at the sign of it, okay? I can, in other words, I can dump charges, okay, into my capacitor, or I can also remove charges from the same capacitor, okay? And when I'm dumping charges into the capacitor, the process is called charging, and the opposite is true. If I'm removing those charges from the capacitor, then the process is called discharging. Okay? So it's a very similar concept. If you think about charging your battery, okay, when your phone battery, right, battery that you use for the phone, and you're basically dumping charges, okay, into your phone. Okay? And when you're using your phone, okay, you're basically removing those charges. So the process is discharging. Okay, so let's talk about this very interesting property called continuity property. Okay, so a very simple thought experiment here. So if I have, let's say if I have a battery, okay, or if I have a capacitor, okay, and I'm trying to charge that capacitor. And one analogy you can think of is, okay, if you have this battery, right, you're trying to charge this battery. So usually it's going to take some time for the battery to go from 0% to 100%. Okay. So instead of saying 0% to 100%, perhaps I can say going from 0 volt to 5 volt. Okay. Just some arbitrary number here. Okay. And if I'm down at 0 volts, then that means the battery is running at 0%. And if I'm at 5 volts, then that means the battery is running at 100%. Okay, so I can kind of use this analogy for my capacitor as well, right? So if I want to charge my capacitor from 0 volt to 5 volt, right? And I have to basically spend some current, okay? I have to expend some current in order for this to happen. Okay? Now, the amount of time that takes for me to charge battery or this capacitor from 0 volt to 5 volt, perhaps, right? So if I make up some number here, it's probably going to go from t equal to T1, right, to T2. So T1 minus T2, right, let's say it's going to be something like 2 hours. Okay, so for example, you're trying to um, um, charge your fully depleted battery, okay, from 0% to 100%, without using a supercharger, perhaps, it will take about the same time, okay, say 2 hours. Okay, so the bottom line here is, for you to go from some 0 volt to 5 volt, right? You're gonna have to spend some time for this process to eventually finish, right? To complete, right? So that you can get a fully charged battery or capacitor. Okay. So what do I need in order to make this happen? Well, I'm going to need the current. Okay, I'm going to need current to charge my capacitor, right? Because dq over dt, right? So I can dump charges into my capacitor so that I can charge this voltage up. Okay, but remember Q is equal to CB, right? Okay, so on the bottom here, I'm plotting I, okay, current divided by C. Okay, so what is current here? So current is C dVC over dt, just from before, and then divided by C. So where I normalize, okay, this C out, okay, so that I can just look at this derivative. Right, so if I take I over C, right, so I have C dVC over dt, so this C and this C can cancel out, so I'm simply just looking at the derivative of this voltage. So in other words, to arrive at this plot, all I have to do is to take a simple derivative of this ramp. Okay, so the derivative of this part is 0, right? So this here is 0, and this ramp here is equal to whatever the slope is. Okay, and this part here again is flat, right? So derivative of this constant again goes back down to 0. Okay, so this denotes the amount of current that I need to charge this capacitor from 0 volt to 5 volt, okay, in the period of 2 hours. Okay, so far so good, right? So this is kind of what we know of and what we're used to, right? So when we charge a battery, we charge a battery or we charge a capacitor. This is a very gradual process, right? It takes time, right? So it takes time. Okay. All right. So I wanted to present another scenario here. Okay. So let's say I wanted to charge my capacitor or battery. Okay, I'm using battery and capacitor interchangeably now because they behave very much the same. Okay. So if I'm charging this battery from 0 volts to 5 volts, okay. So the constraint here is that, well, instead of spending 2 hours, right? Instead of spending 2 hours, I wanted to see if there's a way for me to charge this capacitor or this battery going from 0 to 5 volt in no time. Okay. So in this case, my T1 minus T2 is no longer equal to 2 hours. Okay. So I can define this delta T, which is equal to T1 minus T2, right? So this delta T is no longer equal to 2 hours. I want this delta T to be equal to 0. I want this process to happen instantaneously, suddenly. I want my battery to be charged, or I want my capacitor to be charged from 0 volt to 5 volt all the way, 0% to 100% all the way in no time. Okay. Indicated by delta T equal to 0. So then the question is this possible? Okay. Well, so let's still plot this I over C, right? So I is equal to this C dVc over dt and then divided by C, okay? So basically we are taking the derivative of this plot, of the top plot here, okay? So if you take the derivative of this this sudden jump, right? This is a staircase, right? This is a step function with a sudden jump going from 0 to 5 volts. Then you're going to see that in order for this to happen, you're going to need an infinitely large amount of current, infinitely large, okay? And unfortunately, we don't have that infinite amount of current for us to charge this, or in order for us to make this happen in no time or instantaneously, okay? Because infinitely large amount of current, okay, that you need obviously is not practical, right? So that means this current I has to go to infinity, right? And we can have a very, very large current, but we cannot have an infinitely large current, okay, or a current that goes all the way to infinity, right? A very large current is fine, right? But if we're talking about, strictly speaking, having delta T equal to 0, not even 0.1 or 0.01, then this current has to go all the way to infinity, right? So unfortunately, we don't have the luxury of having this infinitely large current. Okay. So what does this tell us? Okay, so let me go back to this part of the discussion, this part of the lecture notes here. So over here, I define VC at T0 plus, okay, and VC at T0 minus, okay. So for a second, right, so let's assume T0 is equal to 0, right? T is the unit or parameter that we use to denote time, T, right? And I'm going to set this time to 0, okay? So then I'm also going to look at this scale, okay? This is my T. And if I have T equal to 0, I'm sitting over here, okay? And T0 plus or 0 plus denotes the time instance right immediately after 0, immediately after. So if I sort of blow up the scale, that 0 plus is going to sit over here. And similarly for T0 minus, again, if T0 is equal to 0, then 0 minus is going to take place at the time instance right immediately before 0, immediately before. So you'll be sitting over here, 0 minus. Okay. And this is when I zoom in right? So when I zoom in, I can actually see this scale. But when I zoom out, right, actually these 3 points, they basically converge into just one, okay? Because after all, they're all zero, right? So 0 minus 0 and 0 plus, okay? So what this is trying to say here is if you look at V0 plus and V0 minus, right? The voltage that takes place at t equal to 0 plus and the voltage that takes place at t0 minus, they have to be the same, right? They have to be the same, okay? Meaning the voltage drop across the capacitor cannot change instantaneously. It cannot change suddenly. It can change gradually, slowly, but it cannot change instantaneously. So that tells you that momentarily this capacitor, okay, is going to behave like a voltage source, like a battery. Momentarily, it's going to behave like a battery. Okay. And this property is governed by this continuity property, right? It's property of continuity for capacitor. Okay. So this tells you again that if you want to charge your capacitor going from 0 volt to 5 volt, sure, you can do that slowly, okay? But you cannot do it instantaneously, okay? Or such cannot happen suddenly, okay? Nor instantaneously. Okay? Can change gradually, it will take some time, but if you want this to happen in no time, it's not possible, okay? Unless you have an infinitely large current, which we know is not practical, which we don't have, okay, which we don't have. Okay, so this is the continuity property of a capacitor. So by duality, okay, we will have something very similar when we talk about inductor as well. Okay. Okay, so to wrap up the capacitor discussion, um, let's talk about this energy store in the capacitor. So we know that energy is considered as work done. So I use W, okay, to denote energy. If you want, you can also use E, okay, to denote the energy, right? So some people, they like to use E sub C, right? Capacitor energy stored in the capacitor. Okay. Okay, so energy is equal to integral of power with respect to time, right? So instead of using T, I use tau over here as a dummy, okay? So we know this. And power is equal to V times I, okay? Or I times V, okay? Something, all right? And then we also know that from earlier, IC is equal to C dV. So I'll just write it down over here again. IC is equal to C dVC over dt, right? So you see that this uh, important expression keeps showing up many times already, okay? So we have IC, and this can be replaced by C dVC over dt. Okay, and now I have d tau here and d tau there. I can cancel them out. Okay, so now I'm basically doing an integral, okay, with respect to the voltage instead of tau. Okay, so now I need to change my integrand accordingly. Okay, and notice that I have now V sub C at T0, okay, the T0 initial condition, initial voltage, and V sub C at some T. Okay, so when you do the integral and you expand it out, you will find that this is nothing but half CV squared, right? So following this form, half CV squared. But inside here, right, you have VC at T. Um, so VC squared at T, with some T here, minus VC squared at T0. Okay, which denotes again the initial condition. So if there is no initial condition, meaning the capacitor or the battery is fully depleted, then VC at T0 is equal to 0, then equation simply boils down to just half CV squared. Okay, And if there is initial condition, some residual charge sitting in your battery or in your capacitor, then you will have to account for this additional term here for the initial condition. Okay.